So I'm doing my PhD with Xavier Cato and Jonathan Gula in UBO in Brest. A little bit far away from here, but still, it's okay. And so I would be talking about the long-lived deep coherent vortices, and I would explain later why I call them long-lived and the deep coherent, in the sense that I would be talking about the ones which are living below the mixed layer depth, say 1,000-meter depth. And what you see in the background here is the animation of in the full Atlantic basin using 3-kilometer model resolution. And you can see these really fancy vortices which are drifting southwards, and these blue ones which are anticyclones, and you can't see really good, the cyclonic ones, but I would come to that later. So starting with the coherent vortices, what we already know, that they are the circular closed elliptical flows which are generated in particular by the flow instability, and what we can see also from the movie here, which is zoomed in near the Strait of Gibraltar. And what we can see here is that these blue ones are these anticyclonic vortices. They drift southwards because of the beta effect, and these, you can see these cyclonic vortices, they tend to move towards north direction, northwestward. And the scale what I'm using, that lies between quasi-geostrophic mesoscale and the 3D turbulence. And the spatial scale is about 10 kilometers. And the temporal scale is from days to months, and it's I have seen for years too. And the vertical length goes to 1,000-meter depths, something like this. And to tell you about the various detection and tracking scheme, I'm not going further in deep into what has been done in terms of theoretical studies, but how the tracking and the detection approaches have been conducted so far. There are various measures and means which have been opted by people and by the community, where a lot is done on the people have done with satellite altimetry or by Argo floats, and with model approach, people have used occupied parameter, SSH, SLA, that is sea surface height, sea level anomaly, or the vorticity. And these green boxes I highlight because I would be using occupied parameter and the vorticity, where occupied parameter is divide the flow into vorticity dominated and the strain or the deformation dominated region, where the presence of the vorticity is marked by the negative of the occupied parameter. And to give you the details about the numerical setup, what I would be using, so I have used CROCO, that is Coastal and Regional Ocean Community Model, with a horizontal resolution of 3 kilometers. And this spin-up was done for about 10 years, and it doesn't have any tides. Further, the tracking algorithm was used by Mason et al., that is paid by Eddy tracker. And this was originally done at the sea surface, SSH anomaly, but we have adopted along the isopycnal surfaces because the tracking is always done along the isopycnals, or the traces move along isopycnals. That's why we choose not a constant depth, but the isopycnals. Further, we choose 3 isopycnals, 27.60, 27.80, and 27.86. I would brief you later why. Further, we choose the occupied range from 10 power minus 9 to minus 12 because it was catching the vortex, and that was our limit. And the shape error is something that allows the degree of freedom, how much we can allow the vortex to deform. Further, we just skip out the first 3 years because of the spin up, and the detection was done every 12 hours. And the track duration, which I would be showing further before I would show you the big picture of the long lived, what I called. So we see the results of minimum 21 days. So starting with the first picture first, here is the distribution of the deep coherent vortices, what I'm calling DCVs in the further slides. And here what we see is the detection along 3 isopycnals, where the average depth of isopycnal 27.60 lies between around 250 to 1,700 meters. For isopycnal 27.80 lies between 1,200 to 2,800 meters. And for isopycnal 27.86 lies between 2,000 to 4,000 meter depth. Where what we can see over here is that the highest detection takes place at the lowest isopycnal, what is shown over here. And you can see clearly that the most region, like the region which is having highest density, is the region near the coastal boundaries. The cursor is not moving, but you can see it's near the coastal boundaries or near the mid-Atlantic ridge, even in the south and north. Further, and I have written the number of detections which is taking place. So it's in total of cyclones and anticyclones what we see in the Atlantic basin. And what's more interesting, what goes further, when we look for the eddy polarity here is the ratio between cyclones and anticyclones, sum of anticyclones and cyclone. And here, what we see is, first of all, I have only shown here the rate for the tracks which have radius greater than 15 kilometers and Rossby radius greater than 0.1. And that has to match the criteria of at least 50% in their lifetime. And when we see this, we can see the whole ocean basin is dominated by the blue color, that is anticyclonic deep current vortices, whereas we still see some signatures of the cyclonic ones like near the Zepula or near the coastal boundaries. But more or less, and also near, there is a very beautiful thing to see over here when we see near the African coast over here, the cyclonic dominance. And I would come to that too. But overall, the main message is the anticyclonic deep current vortices dominate the major part of the ocean. And now comes the story of long-lived with the west and east and west asymmetry. When we look for the really long-lived ones, where here I'm showing for the vortices which are living for 730 days, that is 2 years. And what we see that the region of formation is, of course, near the coastal boundaries, and propagation is towards west. And the western boundary of is completely quiet because it will hit the topography, so it will not propel towards that side. So generation side is the eastern boundary, and this is the very beautiful view of east-west asymmetry, which needs the statistical view. And further, what we can see very clearly that the number of anticyclonic deep current vortices are far more than the cyclonic ones when we look for the long-lived vortices. And so now what I will do, I will zoom in first to this region with isopycnal 27.60 in the northeast Atlantic basin. Then I would zoom in to the mid-Atlantic region along isopycnal 27.80 and 27.86. So going to this first. So this is the same zoomed in region. And here what we see in terms of detected anticyclonic and cyclonic tracks. I would discuss about the generation mechanism of these vortices. So here what we see that these cyclonic deep current vortices, they don't leave or they don't enter into the big ocean basin. They are very localized. So this effect takes place because of the mirror effect, and they try to propel towards westward but they got clogged because of the topography of the African coast, and they try to escape, but they cannot escape. And that's why because of the mirror effect, the generation near this African coast is like this, and they are trapped here and they cannot go further. And there is another thing. This is the first thing, and the second thing which takes place is near the mid region, where the Medes enter. This animation I showed you before too. And here what happens, the strain of cyclonic vortices, this positive vorticity, and exits the Strait of Gibraltar and moves along the coast, the European coast, and then near the Iberian Peninsula, it just takes the turn, and there is stretching and squeezing of the vertical column, what is taking place over here. And here, what is happening, these anticyclonic vortices are generated mostly over here and near this horseshoe seamount, these anticyclones are sitting here and they are generating. So these big ones are feeding each other and they are getting bigger in size. And these cyclonic ones, on the other hand, they are getting sheared apart and they are unable to live further. And to show you how these anticyclones are looking, to visualize them in terms of horizontal and vertical map. So this is one anticyclone which I have chosen, which I would show even later. So this is just after, say, 3 months after this anticyclone took birth. And the core of this eddy lies in between like 1,000-meter depth, or say 27.60, and that is it. And I have chosen isopycnal 27.6 because this is the isopycnal depth where the midwater enters to the Northeast Atlantic. Where further, this anticyclonic, we can stop this movie. So this one anticyclonic, this is not the only case what I'm showing, first of all. And this anticyclonic MEDI, which is generated here, they are not having a very quiet life when they are living. So they are interacting with different water masses in their whole lifetime. So for example, in this orange, what you can see, this is the one having Antarctic intermediate water, which is generated near the Moroccan coast. Further, it coexists, it doesn't interact. It coexists with the anticyclonic eddy with having Canary water mass. Further, it also interacts with the anticyclones which have cyclonic, these African cyclones. And this is really interesting to see that this anticyclonic MEDI is not having a very quiet life as what we kind of think. And these I have told you about here, this picture about how these cyclonic African coast eddies were getting generated, but how these African coast eddies are generated. For example, these three, they have a very different mechanism, and they are not barotropic. They are generated by the local currents, and we can see that the core is more or less concentrated between 1,500-meter depth and somewhere in between, and they have depth of around 1,000-1,500 meters. And here it's just one interaction what I'm showing, this interaction which takes place where an anticyclonic MEDI and a cyclonic African coast generated MEDI interacts with this. So to proceed on further, I would show you about the mid-Atlantic ridge, which is the most interesting part. This is the mid-Atlantic ridge, and this is along isopycnal 27.86. And the isopycnal, so the depth ranges about 2,000 to 4,000 meter depth, we can say. And what you see, this movie is really, really amazing. This is really slow because the currents are really weak over here. So the major generation mechanism over this place is the topography or the friction, which is also discussed by Molemaker and Desaro in their literature. And there are many articles which I've discussed. So what is really, if we can see really good, then we can see that here, all along the mid-Atlantic ridge, this is the major generation site. And to visualize it in terms of horizontal and vertical map properly, because this movie gets a little bit messy maybe to see. So here I have zoomed in with the horizontal and the vertical map. We can see that these vortices are pretty deep in terms of their core is lying between 2,500 meter depth or say below. Sometimes they are reaching and hitting the ocean bottom and sometimes not. So these are just two examples which I picked to show you guys. And there is another interesting thing, what is happening. For example, what I showed you for the Northeast Atlantic. That is, if we see in the left, this is along 27.80 isopycnal, and the right one is 27.86. And just with our naked eyes, we could see that there are more DCVs generated along 27.86. Further, there are more shielded DCVs along 27.86. And what do I mean by shielded vortices? Shielded vortices is where negative vorticity is getting wrapped, where a negative vorticity having a shield or of positive one, or the vice versa. And what we see over here is that there are many positive vortices having, sorry, the negative vortices having the positive circling around. And there is more interesting thing which is happening in the mid-Atlantic ridge. So that is about the multiplets, and they are transient multiplets. But before to inform you about the transient multiplets, I must also brief you about what are ideal multiplets. So ideal multiplets, they have a particular geometry in terms of a circle or a triangle, or if you say quadruplet, quintuplet, and they form like this. But we see transient multiplets, because, and we call it transient because they are not forming any particular geometry in terms of idealized or how the theory has said. So these are transient multiplets, and what we see that I have a movie too for this. And before I start the movie, we could see that these are organized in one form, like in a horizontal way, then they deform, and then they, from the horizontal, they go vertical, and vertical, they have here the partial merging, then they undergo full merging, and then they finally separate. And this takes about 5 months, 5.5 months for them. And here, for example, this is the first one, second, third, fourth, and you could see that how they come together, and then they, from the horizontal axis, they move to from the vertical, they move to horizontal, they have partial merging, and they have their separate lives after that. There is another example. This is an example of quadruplet, triplet, and duplet. So I have another example of quintuplet, and this is good to see with the movie too. We can see here these 5 ones, and this is a very short animation. We see there is a merging going on, and it doesn't long for very long. It's just for 41.5 days, and they got separated. Unlike this one is for 5.5 months. This is very fascinating. And that's it. And so I would tell you about the ongoing work. So first thing is that with the asymmetry, what I have shown about the east-west asymmetry, there was a question raised by McWilliam in 2016 that why there are more deep anticyclonic vortices compared to the cyclonic ones. And we are trying to address this by saying that they're more stable, anticyclones merge more easily, and they radiate more, and the cyclones radiate more internal gravity waves, which needs to be done. And further trying to understand more better in terms of transient multiplets, because very less work has been done, and the literature doesn't tell a lot about transient multiplets or what we see near the mid-Atlantic ridge. So that's it, but I'm going to end this talk in a very different way. So there is a small summary from my side. It's in this planet with 5 major and mini bays. Standing here is Atlantic for its saga to say. As it extends from north to south, forming deep and intermediate water in the depth with some silent sound. Far away from the surface, but not far from reach, it has some deep swirling flows, which is called deep coherent vortices with real mean, where the boundaries had more birth of place, and they moved along south and north with different pace, and moved more west with hot and cold water in the dress of blue and red, having along Coriolis as their friend. They traveled all along by some bon voyage songs, meeting new friends from country and all abroad, but shining more in the dress, which is blue in form, and deep in the ocean as well, living in the families of shell, and forming the group of transient multiplets, and lived all along for the journey to be felt as a journey to be read.